side to this test. It's all front. It's all problems. The only kind of questions that would be on it would be stuff like, is this endo or exothermic, absorbed or released, spontaneous or not? No short answer, no essay, no fill in the blank. That's it, okay? So it's all math. It's all problems. And in a sense, you should be happy about that because you know how I grade. Unlike the AP exam, which is going to give you almost no partial credit, very, very little. I mean, I took the class, I told you over the summer, I was blown away by how specific they want your work to be, and with the smallest little mistakes giving you very little credit. But certainly there's no possibility of partial credit in multiple choice. Well, I don't grade like that. You give me the work, you show the work like you hopefully did for these first three I'm doing on the review, you're going to get most of the points. You're going to get almost all the points. If your only mistake is a math mistake, you're going to get all but 1 point for that problem. All right, let's start. Let's start with this problem up here. Okay? Now, what I would expect to see on a problem like this is a graph. I reminded you to draw the graph. All right, and it has to be, a lot of people just automatically put the same graph. And that's incorrect. If that's what you have, you lost a point. Okay, why? Because that's not what happened here. That is not what happened here. It did not go like that. Part of that's correct. Matter of fact, most of it's correct. But let's take a look at how much of it is correct. Okay? If I'm making a graph, I'm not just going to automatically look up, oh, he drew one like this in my notes, so I'm going to draw one like that now. I have to look at what actually is happening. It says it starts at minus 10 degrees. There's minus 10. And it ends at 100 degrees. There's 100. Okay? Got it? Make sense? So let's trace what's going on here. If I start at minus 10 and I heat it up, it's going to go up until it reaches what temperature? 0. At the melting point, there is no temperature change, so everything stays the same. Okay? All right. Eventually, all of it's melted, and it will go up and up and up and up again until it gets to 100. It wants me to convert it all to steam at 100, so it's going to look like that, but it will not have anything up here. So if you drew this line up here, you'd be wrong. And let's not forget something, guys. This graph doesn't have to look like that. What if I said it started at steam and it ended up at minus 10? It would be the exact opposite. Start here, do, like that. Okay? So you got to keep in mind, I'm not asking you to just rote memorization, which is, by the way, I want to get off on a little bit of a tangent here. The reason why you guys are having so much trouble, all right, when you're with this review. Yeah, there's a lot of material, but this is only one topic. This is only one topic. The reason you're having trouble, especially for people who didn't have me in the past, you basically, I yelled at you every day last year about, I'm not going to have you memorize something for one test and then forget it forever. We used it all year long. We used significant figures all year long, conversions to moles, grams, atoms all year long, reactions, balancing, electrons. Everything was used all year long. Those of you who thought, well, you covered this 4 months ago. I don't have to know that. Well, right now it was only 1 month ago. It really was about a month ago because Thanksgiving was in the middle. That was about a month ago. Well, you know what? You still have to know how to do it. You don't just memorize it for that one problem and then I'm going to forget about it. And you can't just memorize it for this test and then forget about it. You have to be able to do this. Now, I don't even care what numbers are, but I am going to set up each problem. You would have 4 parts of this: A, B, C, and D. Let's see what you would have had to do for each of these. For part A, you would have had to have used the equation Q equals MC delta T, correct? Where your M, by the way, your M is going to be 10 grams in every case, is 10 grams. Your C is a specific heat of solid water. Where is that? Specific heat C of liquid. There's solid, 4.18. Sorry, solid is over here, 2.09. 2.09 joules per gram degree Celsius. And your TF, I ran out of room here, but the delta T is TF minus TI. Your final temperature, a lot of people do this. Well, the final temperature is 100, so it'll be 100 minus. No, it's just for this segment right here. That's it. That's all A is talking about, right? So your TF minus TI is 0 minus a negative 10. 0 minus a negative 10 is a positive 10. All right, that's why you're going to get a positive answer, which means it's endothermic, which means you're adding energy. And it would be a pretty easy number to do because I have all 10s and 100s, and I told you I purposely made it like that for the review, so you can probably do that one in your head and probably get the answer. but I don't care about the answer. If you show that work, you're getting the credit. For the entire problem, which a problem like this has got to be worth, this test has got to, by the way, be worth more than just 100 points. It's not going to add up to 100. I've got too much stuff on here. It won't be, I don't know exactly what it will be, maybe 120 or something like that, but my point is, losing 1 point for the whole problem that's worth 10 points, that's not a big deal, okay? All right, so that's part A. Let's look at part B. Part B will make him blue. What's that? Question? Problem? Everybody understand that, right? That's what you would do for part A. For part B. Part B is a totally different kind of problem. There is no temperature change here. It is just melting that ice. So all I have to do is take the heat of fusion, which is right here, and multiply it by how many grams I have. So it would be 10.0 grams times 334 joules per gram, and that is it. That's all you got to do. That's how much energy it takes to melt that much ice. For part C, I'd have to do, well, let's just use black this time. For part C, this part here, I would have to, again, use Q equals MC delta T. What's different this time? The C is different, right? The C is now going to be for liquid water, which is 4.184. The mass is the same, it's 10. 4.184. And your temperature change is different. Your TF is now 100. Your initial temperature is 0. 100 minus 0 is 100. And again, so that makes the number pretty easy to do. 10 times 100 times 4.184, right? All right, and finally, in part D, I'll go back to red. In part D, I would have to do this guy right here, where he's vaporized, where I'm basically boiling him. And that would be 2260 joules per gram times 10 grams. And that's your answer. Your answer is all of those added up. So it's too complicated. It is not. You're not 2 years old, people. Adding numbers like this up and doing these problems like this, each one of which is basically simple, is not beyond your capacity. And if you try to figure out that it is, then you're really in the wrong place. You shouldn't be in AP. You have to be able to do that. Okay? You can't pretend that that's a hard problem, because it's not. It actually is a problem from Chem 1. I just reviewed it with you. This is not the hard stuff, all right, in this chapter by any means. All right, so that's the first one. Let's look at this guy here. This guy actually becomes very easy, but you have to know the equation. And here's another thing about this. Here's what you're getting on this test. You're getting Appendix K, all the delta H, delta S, G information if you need. You're getting your card, your formula card. Both pages, of course, you're only using the stuff from thermodynamics, but that's a lot of formulas. I mean, I have them all listed here. All the yellow ones are on here. I mean, that's a lot of formulas. All that stuff, don't have to memorize that either. It's all on there. By the way, I added 2 on here. You know which ones I added? I added this one right here, okay, because it's not on there. And I added the Celsius to Fahrenheit on here, so you don't have to memorize them either. Again, I'm not asking you to do the impossible here. Now, let's get to this problem. What is this equation? Do you remember? W equals negative delta N RT, okay? Negative delta N RT. Now, all you care about here is the change in moles. I said 1 mole of B, which I have a 1 mole of B here, reacting correctly, assuming stoichiometric amounts, and I get the exact reaction happening. I would have to take the change in moles. 2 and 3 is 5 gaseous moles on this side. 3 on that side would be 5 minus 3, so a negative 5 minus 3, right, times R. How do I know R? We've used R before, but not this R. You got to use the right R. This R is in joules per gram, joules per mole Kelvin, which is what you want. And I believe it's, what is it, 8.314 joules per mole Kelvin. All right, and then the temperature, I didn't actually give it to you in this problem, but I told you to assume most of the time it's 298, 298.15. I mean, it's not really important about the 0.15. All right, I assume that if it's at room temperature, that's what you're doing this at. And that's what, I don't care what the answer is. You do all that, you get your answer, whatever it is, you round it off to 3 significant figures if that's what you use, 298. If you use 298.15, you round it off to 4 significant figures. It doesn't really matter, okay? It's not important. So, and again, this is another thing you got to get out of your head. That's why I told you, move on to the next question. Move on to the next question. I told you to do that because a lot of you guys still have in the back of your head that, oh, I keep getting the wrong answer. I mean, I'm used to dealing with that if I have non-honors AP classes, where they just get so focused on the answer. They will literally plug the numbers into the calculator 15 times. I've seen it. I've seen them constantly. I keep getting the wrong answer. The exact same numbers plugged into the calculator. It means nothing. You show me this work. I don't care if you put down 48. It makes no difference. Just make up a number. Granted, you shouldn't do that because you're going to lose 1 point every time you do it. But it's only 1 point. It's not most of the points. It's not even half the points. It's just one lousy point. So who cares what the actual answer is? All right, and finally, this guy right here. I'm going to actually go on. I have it redone over here. Okay? Yeah, you're going to lose 1 point, not all the points. If you can't set up the problem, you're going to lose all the points, as well as the 1 point. All right, that's the last one, and then we're going to stop the camera, and I'll splice these together, hopefully. You watching? Yo. Y'all watching? Now, I could have given you one. I did not. Y'all look up here, please. I could have given you one, but I found this one online. I've done other ones on the board, multiple ones, even a really, really tough one I did, okay, which had maybe coefficients like this, okay, and you had to worry about that. This one does not. All right, all I care about in this case is can you figure out how would I make this reaction from these reactions? And this is about the complexity you'd get from the one on the test. Maybe you'd have a coefficient. That's about the only difference. It's not going to be as hard as that one I gave you, which took us like, 10 minutes to do. All right. I would realize that I've got to have CO2 as a reactant. Right here, this reaction has CO2 as a product. So what do I have to do to that reaction? Reverse it, which means I reverse this. I have CH4 as a reactant. I want CH4. Here is a product. I reverse him. Do I reverse this guy? No. If you do all that, the reason I chose this one because I had them all worked out, they all cancel out except for the things you wanted. You wanted him, you wanted him, you wanted him. Everything else cancels out. That's what you have to show me on these. Notice all of these numbers are reversed where they should be reversed and kept the same where they should be kept the same. Okay? All right. That is Hess's Law. That's a Hess's Law kind of problem. It's not the only way we did Hess's Law. We did a lab on Hess's Law as well. And, of course, even products minus reactions is actually an application of Hess's Law. But when you do like delta H of products minus delta H of reactants. But that is, you're going to see one on the test like that. All right? Everybody good? Okay. Now, yeah, question. All right. Last, I'm going to turn off the camera here because you're going to go on to the next board. This is the review, the second part. Okay? I want you to work on that. We'll go over that in about, this will take us a little longer, maybe a half an hour or so. We'll go over that. Okay. Second part of the review here, you may recognize at least some of these being relatively short, easy problems. Let's take a look at the first two. They should be relatively short, easy problems. Okay? First one, all I wanted to teach you, if you can't do this, if there be a basic problem like this on the test, and you can't do it, I don't know where you've been for a while, because it's pretty much the same thing we've been doing the entire chapter in different variations of it. Q equals MC delta T, right? And I know I have 20 grams. My specific heat, and I didn't give it to you here because I told you it was water. The one thing, everything else is on that sheet. I think by now everyone knows the specific heat of water because it's also needed to do conversions from joules to calories. What is it? 4.184 or 1 calorie per gram degree Celsius. If you use the 1 here, and that's fine, 1 calorie per gram degree Celsius, that's fine. You can then, when you get your answer, convert it to joules, and I'll talk about that in a second. But anyway, it's TF minus TI, right? So your final temperature, it says from this to that, 40 degrees Celsius minus 75 degrees Celsius, all right? And you do the math for that, what's that going to be? All that multiplied together, what do you get?
35.
Everybody get, you say 30? No, total answer at the end.
700.
700. Significant figures as 3 there. Assuming that's correct, 700. Grams cancel, Celsius cancel, calories. Now, I want to do this, because this is important. At some point in the test, you're going to have to also convert from calories to joules. But I don't care if it's 700. All right? I really don't. What's your question?
Negative.
Okay. Oh, yeah. That I do care about. Is it positive or negative? All right. That I do care about. All right. Good point. It's negative. All right. But I also want, I don't want to get too far ahead of myself, but I want to show you how we would convert. Obviously, everybody should know how to convert from calories to joules and back again. Calories in the bottom, joules in the top. What do we know?
1 calorie is 4.184.
4.184. It's one of the few things I'm asking you to memorize because we use it so often, and it's actually multiple places we use it. It's kind of like the numbers, that we have, like Avogadro's number. You kind of should know it by now. All right, Lexi, what did you do wrong? Tell us.
I
Okay.
all I
She
did,
75 minus
I did
40.
75 minus 40 because I think I was just reading it.
Okay, that's important. That's a very big mistake. Y'all hear that? Guys, it's why we're doing this review. It goes from this to that. TF is this, TI is that. You've got to be careful. You're going to get the wrong sign. What else could I have asked you about this? I'm not done yet. What am I going to ask you about this? Endo or exothermic?
Endothermic.
It is not endothermic.
Oh,
It's
sorry.
exothermic. Why is it exothermic?
Negative.
Because it's negative. And that heat is therefore what? Heat is what?
Given off.
Given off, released. Great. Great. All right. Well, that was fun. Now, what about
Whatever.
shh? What about Fahrenheit to Celsius and Kelvin? Pretty easy stuff. Maggie's back there. That's all I can say. Yeah. Girl, I am recording. I would like to use this today. Maggie can control herself. What's the equation for Celsius to Fahrenheit?
Plus 276.
Well, no.
Oh,
Good. That's a good point, though. Let's do that one first.
Wait, can we
Let's do that one first. We have negative 24 degrees Celsius. I want to go to Kelvin first. What is Kelvin's going to be? Celsius plus 273. What'd you get for your Kelvin?
249.
Okay, 249. Now, how would I get Celsius to Fahrenheit? I want to get Fahrenheit. What is Fahrenheit going to equal once you rearrange the equation?
9/5 C plus 32.
9/5 C plus 32. Plug your numbers in, solve it, whatever. That's too easy to waste time on. Let's go to the harder ones. All right? Next one. Molar information equation. There are some mistakes people make all the time in this, and let me point them out to you while I do it. Matter of fact, my guess is a lot of you probably looked at that and had no idea how to do it because we didn't do a whole lot of these. We kind of used molar information equations as a beginning to show you how I got to Hess's Law. But the fact is I can and will on this test ask you one like this, where you're going to have to look up carbon in its standard state. Oops. Carbon in its standard state, which you'd have to write down S graphite. You have to write that down. And by the way, a lot of these guys have weird stuff you have to write down. Some of them are diatomic. Some of them have, like, for example, phosphorus is P4. Some say white. Some say red. Tin. All these guys have different allotropes. So you got to write CS graphite plus, I'm adding H. I can't just put H. I have to put H2 because he's a diatomic element. And that gives me what? C2H4 gas, right? So this guy, I know, has a standard state. It's in the standard state, so his delta H is 0. This guy is in a standard state, delta H is 0. I look in the back of the book. The only guy I have to look up is that guy. What is that guy's delta H information? Is it a positive number?
Yeah.
Point what?
26.
26 kilojoules per mole. I made 1 mole of it. I have a couple of problems now. If I leave it like that, I'm not getting a whole lot of points. What have I not done right now? I haven't balanced it. I need a 2 in front of this. I need a 2 in front of that. I have to put this number. I want you to do this. I want you to put that number on the correct side of the equation. Positive means it's endothermic. So where is that 52 going to go? Over here, plus 52.26 kilojoules, right? Okay, so now you're getting better. Now you got all the points. But I got to warn you about something. I got to warn you about something that you might see on the test. What if I were doing a guy like water I was trying to make, H2O, and I had H2 plus O2? What do I have to worry about there? You see, normally I'm going to balance it like this. I'm going to put a 2 there and a 2 there. You can't do that if I want the molar enthalpy information equation. Because what does that coefficient have to be if I want to make 1 mole of it? 1. So if it's got to be a 1 there, I would have to put a half in front of that, wouldn't I? You see? So that's possible. It may happen. So be careful of that also on the test. Good. So 4th problem. Let's take a look at this guy.
So if it's endo, you put it on the reactant side, and then if it's actually put it on.
Exactly. Back to the previous thing I was saying. If you get a positive value, it's endothermic. That means, again, don't memorize this. It has to make sense. A negative value, you all say, is exothermic. Okay? And that means energy is released. When you write an equation, people, you have to realize it makes sense. A plus B yields C. Yields another way for saying it makes C. It releases C. It creates C. It creates energy. So the energy, if it's negative, is going to be on that side. It's given off. If you're using it, if you're taking energy and turning it into something else, the energy will be on this side if it's a positive value. All right? But either way, delta H, say I get a negative 52. I don't put negative 52 up here. I put plus 52. That's how much energy was given off. You see it? You know what I'm saying? Right? Just so everybody does that is a mistake. All right, heat capacity. What are you going to do here? Again, we're going to go, we're doing okay on time, but we have a lot to go over yet. The other class, I went over this very fast and kind of forgot to do something even, so let's not make that mistake again. You're going to solve for Q equals MC delta T again. And we've used this a bunch of times. We used it in the phase changes. We used it in the previous problem. We used it in this problem. All right? When you solve that answer, I don't really care what you get. Will it be 2,000? That's all I care about. Will it be 2,000? No, it will not. Did anybody actually do it and get a number? What'd you get? How much?
1,171.
1,171, we'll just say. Okay. All right. What do I have to do to get the heat capacity of the calorimeter? Subtract those two. 2,000 minus 1,171. Why am I doing this? The reason I'm doing this, all right, is that that's how much energy must have been absorbed by the calorimeter. Okay? I should have gotten 2,000. That's how much I know was put in there. I only got 1,171 measured. Okay? And I get whatever that is, around 900, right? What do I then do with that 900? Divide that by the temperature change, which is 4 degrees Celsius, and so I'll get whatever I get. How much? 207. Okay. Good enough. Now, this blew people away last period. Because I didn't realize it as I was doing it, but I did add this for a reason. When I watched my video from last time, I realized this. I started going over this problem, and people were like, wait, what are you talking about? That wasn't on the review, was it? No. All right, it wasn't, but there's a problem like it on the test. All right? Now, this is a killer. You've just reviewed now for 2 periods. Read this question. How do you think you would do it without looking stuff up? How do you think you would do this as a review problem? Got to use, this time, you're going to have to use some common sense as well. If there's a problem in the notes, just like it. But instead of looking it up, can you tell me, using some common sense and reading this, how I would have to do this?
Use like 2 equations.
I'm going to have to exactly have 2 problems. This is really 2 things, right? The Q total, right? Remember this? Q total is going to equal the Q from the calorimeter plus the Q from the reaction, right? The Q from the calorimeter I get by taking my temperature change of 2 degrees Celsius and timesing him by, what would you say, 207 it was from the last one, right? That's one part of the heat. The other part of the heat is from the MC delta T. So I'm putting 2 things together here, but you should be able to read that. There is a problem with the M, though.
So is this going like with the other?
Well, this is, don't try pigeonholing things, Lexi. It doesn't go with anything. We've seen MC delta T in like 4 places just in this review. MC delta T is a common equation used to calculate heat changes in a lot of different ways. I haven't even gotten to where I'm solving for TF or where I'm solving for C. All right, I'm going to do those. But the point is, you don't pigeonhole it into, well, this is this kind of equation. This is that kind of equation. You have to think about it. All right, but that's not my point. I have one more point to make on this one. All right, I don't think you're going to get the C wrong. I don't think you're going to get the delta T wrong. I think you're going to get the M wrong. The M is not 50. It's 100 for milliliters. It's still not right because it tells you the density is 1.02 grams per milliliter. So if D equals M over V, M equals D times V, I'd have to take that 100 milliliters, multiply by 1.02. My mass is actually 102. Okay? And I did this exact problem, in your notes from like 2 weeks ago. So if you're saying, I don't remember any of this, how am I supposed to know this? You did know it. You had no problem with it. When we did this in lab, you know how many labs we did with the calorimeters? 4. 4 labs with calorimeters. And yet it feels like we never saw this before in my life. All right, you can't. You have to be able to transfer this information from lab to notes to homework to test eventually. All right. Here. Next one was this one. Is that right?
Yep.
Okay. Delta G. Delta G is our big guy we're looking for, Gibbs free energy, trying to find out whether a reaction is spontaneous or not. Delta H minus T delta S. Don't have to memorize that. It's given to you on the sheet. It will always be given to you on the sheet. Okay. I find for delta H first, whatever he is. I don't care, but it's going to be the delta H of the products minus the delta H of the reactants. You look up in the back of the book. Where are your mistakes coming in these? I'm telling you right now where they're coming from. Looking at where?
No, which ones did you say that it's technically not delta H or
S for S. Even on the top of the paper in the back, it's not delta S. It's S. It's the S's that you're using over here. It's S plus S minus S of products minus S of reactants. But that's not going to be something I'm going to take off for anyway. All right, delta H of products minus delta H of the reactants. 5 mistakes. I'm not going to do them because we don't have time. The 5 mistakes you'll see. Looking in the wrong column. Make sure you're looking at the delta H column, first column. States of matter, gas, solid, liquid. Definitely going to see that as a mistake. Coefficients. Don't forget the coefficients in the equation. This guy's got a 2 there. Which way to do them? Products. I'm looking this guy up first, minus the reactants. Okay, and finally, the math. Keeping the math straight in your head. When I go and do products minus reactants, I better have brackets, and then this guy times 2 plus this guy, all right, in brackets. Do that in my calculator separately so I don't screw that up. That's the least important thing. If you show me all this work, you're only going to lose a point for it, but it's another place to make a mistake. All right, so I do this, and I get my, I do delta H, and I get my answer. Did anybody do it and actually get the answer? What'd you get?
Yes.
Negative 571.
Anybody else get around negative 570 some?
Yeah.
Okay. Then you do delta S of the S of the products minus the S of the reactants. And that guy, this guy's in kilojoules per mole. This guy is going to come out to be in joules. What is he in joules? Did anybody do that?
Negative 205.
205? Somebody said around 205?
Negative.
No.
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 Negative 326.
Negative 326? Okay. All right. Is that right? More people have that one? Again, I don't care. If you find your mistake later, that's fine, but whatever. What do I have to do with that number? I got to convert him to kilojoules.
Can you convert it after you multiply by the temperature in the delta G?
You really should do it before it gets to this equation. It really should. All right? Because otherwise, you'd be doing, I would definitely recommend doing it here. But let's see if you got the right answer if you did it at a different time.
Well, isn't delta S in joules per mole?
Joules per mole Kelvin, right? So you're going to end up with kilojoules per mole Kelvin. Okay? That's all. That's all you're doing.
So, yeah.
You're
I
just
didn't do that until I put it in.
if you did it, even if you did it over here at the very end with the delta G equation, you were probably okay. But just don't forget to do it. Period. So delta G equals, that's a G, believe it or not, delta H minus T delta S. Another mistake. I don't know what T is. Yes, you do. It's eaten with jam and bread. All right, so I take my negative 571 kilojoules per mole minus 298.15 Kelvin times this guy, which was, what was he? Oh, when I convert him, what's he going to be?
Negative 0.3.
Yeah, negative 0.326 kilojoules per mole. Kelvin. Kelvin cancels. I don't really care what the answer is. What do you get for that answer, though? It's going to be negative, isn't it?
Negative 470.
Okay, so let's just say it's negative 400 and some. Let's talk about something. Negative 400, whatever. Let's ask you about this. Is this reaction spontaneous or not?
Yes.
Y'all agree? Okay. Was the delta S, let's take a look at it. The delta S was negative, correct? Let me ask you some questions about this. The delta H was also negative. What would happen as I increase the temperature of this equation? Is it going to make it more or less likely to be spontaneous?
Less.
Right, because I'm going to make the effect of the delta S greater. So at high temperatures, this guy would not be as spontaneous. You understand? Because I'd be making the effect. The T would be making this guy bigger. All right, next. What are we on now? 6? Okay, why don't you at least set this guy up? All right? This is one of those where it's the first law of thermodynamics. You basically have heat lost plus heat gained equals 0. Again, here's another case where I'm using MC delta T plus MC delta T. Only this time I'm setting it equal to 0 because I'm solving for the TF. Correct? Remember doing these? All right, the guy who's losing energy. Some mistakes I will see. I told you not to worry about getting the final answer for this, but just set it up. Okay? Your mass of the guy who's losing heat. Who was the hot thing? That was the iron, right? So the mass of iron is 12.3 grams. That's fine. Specific heat of iron is 0.444 joules per gram degree Celsius. I have to use that one. Did anybody use 4.184 for both of them? No. You have to use that for the iron. And the TF minus TI, what's it going to be? I actually got this wrong last time. What's the TF minus TI in this case for the iron? TF is the unknown. What's my TI?
87.5.
87.5. Okay? Plus, then I got to do water. Water's got 100 grams times specific heat of water. Can I use 1? I don't have a choice in this case. I have to use the same units I used here. Joules here, I got to use joules here, 4.184 joules per gram degree Celsius. And then times by TF minus TI. TF, of course, is still unknown. I'm running out of room over here. Minus the TI, which of water was 20. And I said, don't worry about finish. I mean, obviously on a test you want to finish it, but the review, we didn't have time, so. You're going to combine like terms and all that nonsense. We did this problem before. If you get a math mistake in there, not a big deal. If you have it set up and I can see all that. Okay, number 7, bond energies. I strongly recommend you draw these out, and your prior knowledge of organic will help you here. Somebody else sees CH4, they might panic. We all see it. We see it exactly for what he is. He's methane. We can name him, and there he is. We can draw him out. The Cl2, just be a Cl. CH3Cl, again, people might panic there. I don't think you're going to. You know what CH3Cl looks like in HCl. Okay? So, what you have to multiply by each of these coefficients. You say, there are no coefficients. Absolutely, there are coefficients, aren't there? When I go to multiply these numbers, I'm going to have to multiply the CH bond by 4 times the CH bond. I don't even care what the number is. I told you probably couldn't finish it anyway. 4 times whatever the CH bond is on this sheet under single bonds. Do I multiply this guy by 2 because there's a 2 there? No, just 1 of the CCl bonds. And by the way, notice the difference here. This guy's formula is delta H of the reaction is delta H of the reactants minus delta H of the products. That's why I'm doing them this way. Reactants minus brackets the products. Products being 3 times the CH bond, 1 times the what bond? Not HCl. CCl, don't forget him. 1 times the C plus 1 times the CCl bond. Then you also have plus 1 HCl bond. Okay? Now you don't have to write this out as like you should definitely do this. But here you'd be looking up the numbers in every case, right? Yeah, Maggie.
Are you adding?
Every case, yes, you're adding here, subtracting from this big thing, adding, you add all these guys up, you add all those guys up.
So we don't multiply the CH3Cl one.
You do. I multiplied it by
Like
3.
the whole thing.
Well, yeah, I can't. I have to look at what bonds I'm talking about here, right? I have a CH bond, and a CH bond. That's why it's 3 CH bonds. I have 1 CCl bond, and I look those numbers up. All right, next. Almost done here. Couple more to go. Just enough time. What the heck? Did I skip one?
Nope, wait, that's it. I think we're good.
Yeah. Come on. I don't know how that got in there. Wow. There was a number 8, right? Oh, I know why number 8. It was just a question, right? Okay, let's go back to that. Okay. So let's talk about number 8. H2 2H2 plus O2 yields 2H2O. All right, they're all gases. Was this guy basically negative or positive work? Positive or negative work? And how do you know? Why? Yeah, work was done on the system because I started with three total gaseous moles on this side, correct? I only made 2 on that side. So that guy was compressed, all right? He didn't do work. Work was done on him, all right? And that would be positive. How about the combustion of propane? I didn't even write anything out. Well, let's write out the combustion of propane. Combustion of propane would be C3H. What's propane? C3H. What's it going to be? 8. Plus what? Very good. Plus what? Combustion of propane means I'm adding oxygen to it, correct? Yields 2 products, assuming they're all in gaseous form. CO2 and O2, right? Carbon dioxide and water. Sorry, not O2, H2O. CO2 and H2O. Carbon dioxide and water are the 2 products from any combustion reaction. So just asking something like this, don't let that throw you. Now, by the way, can I look at the number of moles yet? No. What do I have to do to this guy? Balance it. I'm not going to. You could do it on your own if you want to, because we have 1 minute left. I want to get to the last one. The boiling point and temperature range of spontaneity. Let's talk about that for a minute, okay? That comes down to, I know the bells and ring, you want to stay here for a second. Delta G equals delta H minus T delta S. You had to do this section on your own. I know from talking to most of you walking through the door, you did not, okay? You need to look this over. There's 2 kind of problems you're going to get here. I already hinted at one of them already, where you have to look at the size, or I'm sorry, the sign of both of these guys. Can you do that? Can you tell me which guy? Look here. Can you tell me which guys are always spontaneous, never spontaneous, spontaneous at high, spontaneous at low? It's not enough. Yo, listen, before you go. It's not enough to just be able to tell me that. If you look at the questions I told you to do on your own, you're going to have to set delta G equal to 0 and solve for T. And then tell me above that temperature or below that temperature, is he spontaneous or not? Okay? So that's what that meant. Those last 2, boiling point. And one last thing about boiling point, people, look here. What if I asked you to calculate that boiling point of water, for example? I don't know the equation. Yes, you do. You know what the equation for the boiling point of water is? Look, wait. Everybody agree? That's the boiling point of water? Where liquid water is turning to gaseous water.
Oh,
Okay, goodbye.